In Chapter 6, we'll study some approximation theory, beginning with orthogonal projection. We'll study regression analysis, scene analysis, and rational function approximation. And finally, we'll consider rank 1 matrices and structure tensor. Okay, the first section of the chapter is orthogonality and the Schmidt process. Okay, this section is a review of linear algebra. We define the orthogonal projection for a given non-zero vector u. We choose y on arbitrary vector. Then we try to decompose the vector y into two components. One is parallel to u, and the other one is orthogonal to u. And we start with, okay, now y hat is alpha u, so that y equal y hat plus z. Then if we use alpha u, because it's parallel to u, so y hat can be written in this form. Then from here, first we have to decide alpha. In order to do that, we try to make dot product with u, then y and u equal alpha u dot u plus z dot u. Then z is orthogonal to u, so we said this is 0. Then from here we can get alpha is y dot u over u dot u. So we have this formula. And we found alpha such that the remainder part is orthogonal to u, so that we decide this alpha. And once y hat is subtracted from y, then z is the remainder part, which is orthogonal to u. In this case, the vector y hat is called the orthogonal projection of y onto u, and z is the component of y orthogonal to u. But if we try to deal with this orthogonal projection more effectively, and we may try to define orthogonal projection to the space rather than a vector. So let's define L spanned by the vector, the single vector. Then this is a line including the vector u. Then this projection can be considered as the projection onto the line rather than onto the vector. So we may consider this projection the projection to a space. So we use this notation, projection of y onto L. Okay, that is the definition. And with this background, we can make this orthogonal decomposition theorem. Okay, W is a subspace of Rn. Then each y, an arbitrary y in Rn, we can express it uniquely in this form: y equal y hat plus z. Y hat is in the space W, and z is orthogonal to the space. That is called W perpendicular. So you can call it W perp. And that means that z is orthogonal to every vector in W. So we have decomposition. One is in W, the other one is orthogonal to every vector in W. If we have an orthogonal basis for W, then for the bases, we may try to get the projection quite easily. So its y hat is projection of y onto the subspace W. That can be written in this form. And then now the projection is subtracted from original vector y, then the orthogonal component can be found in this way. I believe most of you learned this one from linear algebra. Pictorially, we can see this way. Now, y is an arbitrary vector, and W is this green area, is a subspace. Now, this y will be projected onto the subspace, and that will be y hat. And this orthogonal component, which is y minus y hat, is z here. So y can be expressed as y hat plus z, right? Okay, let's see properties of orthogonal decomposition. Y is y hat plus z. Now y hat is in W, a subspace. Z is in W per. Then y hat is called the orthogonal projection of y onto W, and we can write in this form projection of y onto W, right? And y hat is the closest point to y in W. In fact, this is in this sense, y minus y hat length is minimum among all vector v in W. Let's go back to the figure. Then y hat is the projection. And now from y, if we choose any v on W, any v, the length will be not less than this y minus y hat. So it is the closest point to y in W. Right? Okay, y hat is called the best approximation to y by elements of W. We are rewriting this second claim. If y is in W, then its projection is not changing. Already it's in W, and projection to the subspace W should not change the projection. Okay. So if you apply projection twice, then it's the same as one application. Okay. Here we have a proof for this. The orthogonal projection can be viewed as a metric transformation. This means that the orthogonal projection can be expressed by a metric multiplication. So that is an exercise for you. Now we'll consider the Schmidt process. Schmidt process is an algorithm to produce an orthogonal or orthonormal basis for any non-zero subspaces of Rn. Now, once you have a subspace, then subspace should have a basis. From the basis, you can produce an orthogonal basis. If the orthogonal basis is normalized, then it will become orthonormal. Okay, see this example. Now W is spanned by two vectors, x1 and x2, and x1 is given in this way, x2 is now 1 to 2. Find an orthogonal basis for the subspace W. Okay, here for this problem, the key idea is orthogonal projection. We start with x1 and x2. Of course, they are linearly independent, so that x1, x2, these two vectors form a basis for W. Now, along with this basis, they are linearly independent, so that we try to make x2 projection to x1. So it is alpha x1 that is a part of x1 in the direction of x1, and v2 will be orthogonal to x1. So that is orthogonal projection. Now we name this one as v1, and then now we write here now v2, and then that is x2 minus projection of x2 onto the space of x1. So this is rewriting of this equation. Now, once we rewrite this way, then these are clearly independent, and then now in fact these are orthogonal. And this space is two-dimensional, so that once you try to span the space from v1, v2, then that will be the same as original space, and they are orthogonal. So these two vectors will be on orthogonal basis of the space W. Okay, we'll compute the alpha easily. Here for that one, this alpha must be x2 dot x1 and x divided by x1 dot x1. Then from given vectors, you can get easily this quantity. So it's 1/3. So v2 is x2 minus 1/3 of x1. So we can reach this one, 002. Visually, we can interpret that computation. Originally, now here we have x1 is here, and then there is x2. It's a real scale in 3D coordinates, and x2 is projected here. And now orthogonal component is this one, v2, which is now 002, so that it's an upward vector. So rather than x1, x2, we are trying to get now x1 renamed to be v1, and this orthogonal component, which is v2. So v1, v2 will become another basis, but now it is orthogonal. Okay, that's the idea of Gram-Schmidt process. We can generalize this process for arbitrary number of linear independent vectors. Okay, yeah. The Gram-Schmidt process given a basis x1 to xp for a non-zero subspace W of Rn. Basis means that none of these vectors are zero vector, and also they are linearly independent, and linear combinations will span the given space. Okay, that is basis, and we define exactly the same as in this one. So the first step is v1 is x1 and v2 is x2, and subtracted by projected to v1, so that projection is in fact the projection to the space of a v1 that is subtracted. Okay, so far exactly the same as earlier in example. Now we expand this one to a third vector. Now x3 is projected into v1 and v2 and the first two vectors, and that component is subtracted from x3, then the orthogonal component is v3, is non-zero, because from the beginning, we assumed that these are linear independent, so that we have always left over, which is orthogonal to the previous subspace. In this way, we are making again new vectors and orthogonal each other. Now, let's look at here v1, v2. Span by v1, v2 must be same as span by x1, x2, because v1, v2 is also a linear combination of x1, x2 and orthogonal. So it must be, now the span must be the same space. And again, even though you add one more, here the space spanned by these 3 vectors must be same as the space spanned by the 3 vectors. Keep going, and then we can reach at the last vector. So that is the Gram-Schmidt process. The idea is, for a given vector, we try to project it into earlier orthogonal space, and then this projection is subtracted. Of course, the projection is orthogonal projection. Then a leftover remainder part must be orthogonal to the earlier space, and that will be chosen to be the new basis entry. Okay, that's the Gram-Schmidt process. Okay. Now, after getting these orthogonal vectors, once they are normalized, which means some scale by is magnitude, so that it becomes length 1, then that'll be on orthonormal basis. And it's often implemented for the normalized Gram-Schmidt process. That means that usually once you call Gram-Schmidt process, then your output is orthogonal basis, but also it's orthonormal. So it's normalized. After normalization, it is produced. In fact, during the computation, and each time it is normalized, so that is after getting V1 is normalized. Then now when we try to get x2, this is not necessary, because this dot product will be 1, so that we can get easily V2. And again, V2 is normalized. And then these two are not necessary, and so on. That's the reason it is often implemented along with normalization. Okay. Okay, for these 3 vectors, it'll be a good exercise for you finding on orthonormal basis. Okay. Okay, thank you.